few words about our computer vision laboratory, short introduction. Our research focuses on computer vision processing using the mix of classical and deep learning approaches, but not only for RGBD images, but also for other spectrals like depth, infrared, or thermography. What is characteristic for our research? We create algorithms that can operate using HII devices, especially for robotic purposes. The goal of our project is to define and evaluate the capabilities and possibilities of data processing directly on board of the rover to reduce transfer needs between the rover and the ground station, and to increase the robot autonomy in the future. We divide our project into 4 parts. Firstly, we developed deep learning algorithm for rock segmentation of the lunar surface. So we have images from the rover on the surface, and we segment where the rock are. Then we deploy the model using HII device with FPGA accelerators. Next, we integrate the model, rover hardware and software together on rover. And finally, we test our platform during the analog lunar mission. What is important, the project timeline was only 6 months. So this project is in the line with the new space paradigm, in which we don't use special qualified devices to perform our project, but we use consumer-grade devices. There are a lot of benefits. The first of all, the reduced time and cost of the project, then more rapid innovation, and what is more important, the new space paradigm allow for research by startups and scholar and universities, so it can make the lunar exploration better for everyone. Edge AI devices have some of features. The most important is the onboard processing. So we don't stream any data between the device and our cloud or every otherwhere. So we have the perma latency, and we have improved privacy. Then we can operate offline, so we can apply some of autonomy where we request some operation for the rover and then wait for the response. This is very important when we have a long space between the rover and a ground station. And what is the most difference between HII devices and general purpose GPUs and cloud GPUs? HII devices have very high ratio between the performance and power consumption, so we can make the inference more efficiently. But there are also a limitation. When we create the deep learning algorithm for HII devices, we can't go over some barriers of available processing power, memory, and storage. We also can't do many inference at the same time. The most often is at most 2 inference at the same time. What more, the frameworks for HII devices have some limitation with the support for deep learning layers. So each framework has a table, what layer is available or not available. And with HAI devices, often we have to quantize model waves. So we cast or transfer the weight from the floating point precision to integer precision, int8 precision, or lower, sometimes binary precision. I prepare examples of HAI devices. The first is NVIDIA Jetson family. It is the most popular for autonomous driving now. Next are devices from Xilinx or AMD now that provides FPGA acceleration, and microcontrollers with AI devices, AI accelerators included. In the second row, we have some accelerators which have to be plugged into other computer and often also enable the inference of deep learning, for example, on Raspberry Pi. I searched for some HAI devices that are already deployment for the space. I found 3 examples. First is the Raspberry Pi Zero used on CubeSat to control the rotation and position of the satellite. The second is a Gauss constellation, where in which all of satellites, the Jetson Xavier was added to perform large-scale inference of hyperspectral data for weather observation. And I found the Moon Ranger mission that used NVIDIA Jetson TX2 for computer vision task, but the launch of the rover is already delayed for the end of this year. So to be in line with the new space paradigm, in our project we also use consumer-grade robot. Here is a Husky rover. We extend the rover with the lights, IMU, and cameras. And what's more, we replace the onboard host PC computer with the FPGA board to make the operation more efficient and reduce the power consumption. The whole system of the FPGA was merged using the robot operating system. ROS is a framework that provides a set of tools and ways how to perform robotic tasks. What's more, ROS also is now with the new space paradigm and create the sub-module named Space ROS, in which the core of the functionalities are rewritten to be aligned with the aerospace standards. And here is the scheme of our system. We have the main node that that control the whole operation, and then we have 4 helping nodes. First is the driver node to communicate with the robot, with the engines. Then we have accelerator node to read the speed and etc. And here we have camera node to read the RGB data. So we have visual data and the depth to the object. And here is our AI engine node that communicates with DPU. In this case, is the FPGA accelerators. And now I talk about our model deployed on the DPU. Our research is based on artificial lunar landscape dataset. It has 2 parts of data. First is a synthetic data generated by graphics tools and is used as training set. for each images, the mask of each rock was generated together with the synthetic data. And here is the real part of the data set from the using the real images from the lunar surface. And it is used as a test data set. And here is our network architecture. With the limitation in head, we create the UNet network, but it has only 2 depths. And as you can see, it uses the classical layers because of limitation of FPGA accelerator. For image in input, we generate a mask, one-channel mask with the probabilities of the rock is present. We use sigmoid activation. What is interesting, sigmoid activation is not implemented for FPGA accelerator, so it's performed outside of the network in CPU. As a loss function, we use dice focal loss to make the segmentation reliable as is possible, and with the not blazed borders. And here we have our result. This is a dice score. What is dice score is a F1 score for a segmentation task. We reached the result about 0.7. As you can see, there are 3 rows of results. First is the float stage. It is a raw output from the network on our PC computer. Then we have a quantization stage when we translate the weights from the floating point into the integer. And then we have a compiled stage when the weights together with the model architecture are compiled to the FPGA accelerator. And this result is from FPGA onboard. As you can see, after quantization, we increase the results in bit. It can be due to generalization of the weights from some images. Here is an example prediction from the synthetic part. As you can see, it is almost perfect, but it's only synthetic. Here we have example prediction from real part. As you can see, algorithms work pretty well for the rocks are a little bigger and closer. And for this processing, we used depth information in next steps to define if this rock is closer but is smaller, or this is the large rock but is far. And final step, we perform testing on Lunar Research Station. The Lunar Research Station is placed near Piła, Poland, in a post-Soviet nuclear bunker. And here is an example from inside. We perform several tests inside, many scenarios with various light conditions. Here is an example of an image from the onboard robot, and when we collecting the images, we label it many of them and create our data set to validate how the algorithm can operate in the Lunar Res station by metrics. And here we reach the dice coefficient at the level of 0.65. As you can see, this time, after quantization and compilation, we have a little decrease in the results. And here is an example prediction from Lunar Station on the images from the robot. These images are captured directly from the onboard the rover, and then we inference at the same time and only stream the mask outside of the rover. And this project was founded by European Space Agency, and we perform it together with our partners from KP Labs, and thank you.